Welcome to our second lesson in kinematics, this one on velocity time graphs. So let's get some of the theory behind velocity time graphs. Whenever you have a velocity time graph, if you have a positive gradient, it means that your object or person is accelerating. The steeper the gradient, then the greater the acceleration. If you have a horizontal line, then unlike the displacement time graph, it does not mean that your object or person is stationary, but rather it means that they are moving at a steady speed. The only time a horizontal line will mean that the object or person is not moving is if that horizontal line portion of the graph is on the time axis itself. If you have a negative gradient above the x-axis, then it means that you are slowing down, or there is deceleration, in other words. If your graph is below the time axis, then that is a negative velocity, which means that actually the object is moving in the opposite direction. So if you have a line sloping downwards in the portion of the graph that is below the time axis, which is negative, the two negatives means that it's actually speeding up, but in the opposite direction. Okay? If you have a horizontal line below the time axis, that is also a steady speed, but once again, it is in the opposite direction. When it comes to a velocity time graph, we can also find the gradient. The gradient would be the acceleration, right? So if it's positive above the time axis going up like that, it's a positive gradient. If it's a horizontal line, that means there is a constant velocity, and so it is an zero acceleration. And if it is sloping downwards above the time axis, that is a negative acceleration, also known as deceleration. Another thing that we can use a velocity time graph for is to find the total distance traveled. And in this case, it would be the area under a velocity time graph. So whenever you're finding the total distance traveled, all you need to do is to find the area under the velocity time graph by breaking it up into different pieces. The most common pieces that you will be breaking up the graph into are a triangle and a rectangle. Okay? So you just work out the area of each of these shapes, and then you add all shapes together, all the sizes, and you will get the total distance traveled. So you might be asking, but how is it that the area under a velocity time graph gives you the distance traveled? Well, let's take a look at the units. So if we have velocity, which is measured in meters per second, and you have time, which is measured in seconds, when you are finding the area, you will end up multiplying the velocity and the time. The units would be meters per second multiplied times second. What would happen here? The meters per second and the second would cancel each other out, and you're left with just meters. So that is why you are left with just the distance traveled. Another way you can look at it is velocity is distance over time. If you rearrange that equation, distance would then be equal to velocity multiplied by time. Let's move forward now. Let's look at an example. Let's say we are asked to describe this journey that we see here in words. We're also to determine the velocity using this graph when the time is 2 seconds and 4 seconds. Also, we're to determine the acceleration for all three parts of the journey. And in addition to that, we're to find the total distance traveled and the average velocity of the journey. So let's begin with part one. If we're to describe this journey in words, we can say that the person travels from the origin with uniform acceleration for 3 seconds. They then travel with uniform velocity for a further 2 seconds. Right? And we know it's 2 seconds because that's the difference between 3 and 5. And finally, they travel with negative uniform acceleration, or you could just say deceleration. What would be the velocity at time 2 seconds? Well, to determine that, you go on 2 on the time axis and you find the corresponding velocity, which in this case would be 10 meters per second. What is the velocity at time equals 4 seconds? Same thing you do, go up to the graph and go straight across, and it corresponds to 15 meters per second. Next, let's see what the acceleration is for all three parts of this journey. So here, the acceleration for OA is the change in velocity divided by the change in time. You could also have said it is the gradient. Same thing, right? y2 minus y1 over x2 minus x1. So here, the change in velocity, it goes from 0 up to 15. So that's a difference of 15. And then the time goes from 0 up to 3. So that's a difference of 3. So 15 divided by 3 gives us 5 meters per second squared. Remember that the velocity is in meters per second, and we're dividing that by the time, which is in seconds. So meters per second, or simply meters per second squared. How about for AB, the section AB of our journey? Well, no calculations are necessary for that. You should simply state that it is 0 meters per second squared. Anytime you see a horizontal line on a velocity time graph, the acceleration is always 0 meters per second squared. Keep note though, that does not mean that it is stationary. It is just not changing in velocity. So it is possible that an object could be stationary. If it is stationary, its velocity isn't changing. But it could also mean that it is moving along at some other speed, such as maybe 15 meters per second, and it is not increasing nor decreasing. So it is not accelerating. In either case, the acceleration for a horizontal line on a velocity time graph is 0 meters per second squared. Finally, the portion BC of our journey. The acceleration is the change in velocity divided by the change in time. So here now, it goes from 15 down to 0. So 0 take away 15 is negative 15. And then the time goes from 5 up to 8. So 8 take away 5 is 3. So negative 15 divided by negative 3 gives us negative 5. So our acceleration is negative 5 meters per second squared. Next, the total distance traveled. So let's take a look at our graph here. We can break it up into three parts. We have a triangle, we have a rectangle, and we have another triangle. So the formula for the area of a triangle is half base times height, and that of a rectangle is length times width. So in our first part of the journey, the base is 3 seconds, and the height is 15 meters per second. The rectangle now, the length and width, you could say, are 2 and 15. And luckily for us, in this example, it's symmetrical. So the other rectangle has the same dimensions, 3 by 15. So a half of 3 times 15 is 22.5. 2 times 15 is 30. So 22.5 plus 30 plus 22.5 gives us 75 meters. But wait, we could have done this a different way. Let's say you want to do it quickly and easily in one basic step. You could look at this graph and see overall just one trapezium. What is a trapezium again? It is a four-sided figure that has one pair of parallel sides. The formula to find the area of a trapezium is 1/2 times a plus b in brackets times h, where the a and the b are the two parallel sides and h is the perpendicular distance between those two parallel sides. So here, our a and b, we could say a is this parallel side which has a length of 8, b is this parallel side which has a length of 2, and then h is the perpendicular distance between them, which is 15. So 8 plus 2 gives us 10. A half of 10 is 5. 5 times 15 gives us 75 meters. No matter which way you slice it up, dice it up, or do it as a whole, you should still get the same correct answer. So, next, the average velocity. Well, what is average velocity? Average velocity is the total distance traveled divided by the total time taken. So, what is our total distance traveled? As we found, it is 75 meters. What is our total time taken? Right from our graph, that is 8 seconds. So the average velocity will be 75 meters divided by 8 seconds, and that gives us 9.375 meters per second. Rounded off to 2 decimal place, 9.38 meters per second.